There is a star in the night sky that has been dying for longer than our civilization has existed. You can see it without a telescope. You can find it with nothing more than your own two eyes on a clear winter night, a faint reddish point, sitting at the shoulder of Orion, burning with the light of 100,000 suns. Its name is Betelgeuse. And if the numbers are right, if the signals we have been watching, quietly, carefully, with growing unease, are telling us what some astronomers now believe they might be telling us, then we are living inside the final chapter of its life. Not the final chapter measured in geological time, not the final chapter measured in the slow, indifferent arithmetic of stellar evolution. The final chapter measured in something far more immediate, something that sits uncomfortably close to the length of a single human memory. 4 years. Give or take the margin of error that separates a confident prediction from a catastrophic surprise. 4 years until the sky changes forever. 4 years until something that has never happened in recorded human history happens directly above our heads, close enough that people with no interest in astronomy will walk outside, look up, and understand, without being told, that something enormous has just ended. This is not a certain prediction. Science does not deal in certainties when it comes to the deaths of stars. What science deals in is evidence, pattern, and probability. And right now, the evidence surrounding Betelgeuse is stranger and more compelling than it has been at any point in the 4 centuries since Galileo first turned a telescope toward the sky. The patterns are converging in ways that make certain researchers deeply uncomfortable. The probability distribution, which once spread across tens of thousands of years, has in the minds of some observers begun to compress towards something almost shockingly near. And so, this video is not a declaration, it is a countdown, a speculative, carefully constructed, scientifically grounded countdown to the most spectacular event the human eye may ever witness. We are going to walk through every phase of what is coming. Every stage between now and the moment Betelgeuse either proves the skeptics right and continues burning quietly through our lifetimes, or proves something far more astonishing, that we are right now in the last handful of years before the nearest supernova in 4 centuries rewrites the night sky. Let's start at the beginning. Not the beginning of Betelgeuse's life, though we will get there. Let's start at the beginning of why anyone is talking about a 4-year window at all. Let's start in the autumn of 2019, when the star began to do something it had never been observed doing in all the decades of modern astronomical measurement. It began to go dark. Betelgeuse is what astronomers classify as a red supergiant. It sits roughly 700 light-years away from Earth, which means the light reaching your eye tonight left that star around the year 1325, when the Aztec Empire was still young and Europe had not yet experienced the Black Death. At that distance, it is close enough to be the nearest red supergiant to our solar system, and close enough that if you replaced our Sun with Betelgeuse, the star's outer atmosphere would extend past the orbit of Jupiter. It is not merely large, it is large in the way that makes the word large feel insufficient. Its diameter is somewhere between 700 and 1,000 times the diameter of our Sun, depending on where you measure the boundary of its diffuse, pulsating outer layers. If our Sun were the size of a basketball, Betelgeuse would be roughly the size of a 6-story building. It contains somewhere in the range of 10 to 20 times the mass of our Sun. It burns so hot and so violently at its core that it is consuming itself at a rate our Sun will never approach. And that consumption, that furious, unsustainable burning, is the reason Betelgeuse is dying. It is dying because it was born too large, too bright, too powerful to last. Stars like our Sun can burn for 10 billion years. Betelgeuse has been burning for only about 8 to 10 million years, and it is already in its final stage. By stellar standards, it lived fast, and by stellar standards, it is about to die young. The dimming event of 2019 and into 2020 is now referred to in the astronomical literature as the Great Dimming. This was not a minor fluctuation. Betelgeuse is a variable star, meaning its brightness rises and falls in predictable cycles, and astronomers had been tracking those cycles for well over a century. The star pulses with a primary rhythm of roughly 420 days and a secondary rhythm of about 2,200 days, and within those rhythms its brightness can vary considerably without any cause for alarm. Variable behavior is normal for a star like this. What happened in late 2019 was not normal. The star's brightness dropped to the lowest level ever recorded in modern astronomical history. By February of 2020, Betelgeuse had dimmed to roughly 40% of its usual brightness. It had faded so dramatically that it was no longer even among the top 20 brightest stars in the night sky, a ranking it had held comfortably for as long as human beings had been cataloguing such things. Amateur astronomers noticed the story broke into mainstream media, and for a few weeks there was a genuine, widespread, publicly visible conversation about whether we might be about to witness a supernova. The consensus that emerged afterward was reassuring and, in retrospect, perhaps slightly too comfortable. A team of researchers determined that the dimming was caused by two overlapping factors: a cooling of the star's surface temperature and a cloud of dust that Betelgeuse had ejected from its own outer layers, which then condensed and partially blocked our view of it. The star, in other words, had sneezed. It had ejected a plume of material had cooled into dust, and we had been looking at the star through a veil of its own making. By April of 2020, Betelgeuse began to brighten again, and the consensus solidified. No supernova imminent, the star was behaving unusually but not terminally. Everyone could relax. But here is where the story becomes more complicated. Because Betelgeuse did not simply return to normal after the Great Dimming, what happened next is the part that does not get discussed as often in the popular press. The part that sits at the centre of why certain researchers are now looking at timelines that feel uncomfortably short. After brightening again in mid-2020, Betelgeuse did something unexpected. It began brightening beyond its normal range. By early 2021, it was outperforming its historical brightness averages significantly. Then it dimmed again. Then it brightened again. The oscillations became more erratic, less predictable, less consistent with the well-documented pulsation cycles that had defined the star's behavior for as long as we had been watching it. The 420-day pulsation cycle, which had been the star's most reliable rhythm, appeared to be disrupted. Some researchers noted that this disruption itself might be a signal that the internal dynamics of the star were changing in ways that the surface behavior was beginning to reflect. Then came a paper, published in 2023 by a team of Japanese researchers affiliated with Kyoto University. The paper drew on a combination of observational data and stellar evolution models to make a claim that was, by the standards of academic astronomical literature, quite striking. The researchers argued that the behavior of Betelgeuse, the Great Dimming, the subsequent erratic oscillations, the disruption of its pulsation cycles, was consistent with the behavior expected of a red supergiant in the very late stages of oxygen and carbon burning in its core, not the final stage, but close to it. They proposed a timeline. And they suggested that based on their models, Betelgeuse could be within a few decades of its terminal event. Some interpretations of that paper, particularly in the popular science press, compressed that window further, into single digits of years, into something that felt startlingly near. The scientific community's response was measured, as it always is. Other researchers pushed back. The uncertainties in stellar evolution models are enormous. The internal state of a star 700 light-years away is not something we can measure directly. We are always reading the surface and inferring the interior, and that inference involves margin of error stacked upon margin of error. But the pushback did not erase the paper. It did not dissolve the data. It simply placed a question mark beside a set of observations that had not existed in quite this form before. And that question mark is still there, hanging in the literature, in the conversations between researchers, in the quiet unease of people who spend their careers watching this star and who have begun to feel that they are watching it differently than they were 5 years ago. This is the context for our countdown, not a certainty. A possibility, given urgency by data we cannot ignore and humility by the limits of what we can actually know. The 4-year window is speculative. It is the near edge of a range that extends much further. But it is not invented. It is not fiction. It is the shadow cast by a body of evidence that keeps accumulating, that keeps pointing in the same direction. And that has prompted some of the people closest to this data to say, quietly, that they would not be entirely surprised. That is the threshold we are standing on, and from here we are going to walk through everything that follows. To understand what is coming, you need to understand what Betelgeuse actually is right now, at this moment, in terms of its internal structure. Because the story of a supernova is not a single event, it is the final act of a process that has been running for millions of years, moving through stages with the unhurried certainty of something that was always going to happen, that could not have been otherwise. That was written into the physics of this star's existence from the moment it ignited. And we are somewhere inside that process right now. The question is, how far inside? A star lives by balancing two forces. On one side, gravity, the inward pull of all that mass trying to collapse the star under its own weight. On the other side, the outward pressure of nuclear fusion in the core, the energy released by fusing lighter elements into heavier ones, which pushes back against gravity and holds the star in a state of suspended tension. This balance is the definition of a living star. When the balance holds, the star shines. When it breaks, the star dies. The way it breaks determines how it dies, and for a star the size of Betelgeuse, the way it dies is as dramatic as physics allows. Our sun fuses hydrogen into helium. That is its primary fuel, and it has enough of it to keep burning for another 5 billion years. When it eventually exhausts its hydrogen, it will expand into a red giant. It briefly fuse helium in a shell around an inert carbon core, and then shed its outer layers into a planetary nebula, leaving behind a white dwarf, a cooling ember about the size of Earth, slowly fading over billions of years. Our sun's death is quiet by cosmic standards, gentle even. Betelgeuse's death is not. Betelgeuse is massive enough that it does not stop at helium fusion. When its hydrogen was exhausted, it moved on to helium. When its helium was exhausted, it moved on to carbon. Carbon burning produces neon and oxygen. Then the star burns neon. Then oxygen. Each stage produces heavier elements and releases progressively less energy per unit of fuel, which means each stage runs faster than the last. Hydrogen burning in a star like Betelgeuse takes millions of years. Helium burning takes hundreds of thousands. Carbon burning takes thousands of years. Neon burning takes about a year. Oxygen burning takes months. And the final stage, silicon burning, which produces iron, takes approximately 1 week. Iron is where it all ends. You cannot fuse iron to release energy. Iron fusion consumes energy rather than releasing it. When a massive star accumulates an iron core, the outward pressure of fusion drops suddenly and catastrophically, and gravity wins instantly and completely. The core, which may be roughly the size of Earth but contains more mass than our Sun, collapses in less than a second. The outer layers of the star, still enormous, still largely intact, begin to follow. And then they hit the collapsed core, which has become so dense that it bounces back the infalling material with a shock wave of almost incomprehensible violence. That shock wave travels outward through the star at a significant fraction of the speed of light. When it reaches the surface, the star explodes. Every layer of material that was once part of Betelgeuse, the hydrogen, the helium, the carbon, the oxygen, the neon, the silicon, gets blasted outward into space at velocities of up to 30,000 kilometers per second. The energy released in that explosion exceeds what our Sun will radiate over its entire 10 billion year lifetime, all of it in seconds. That is a supernova. The question of when Betelgeuse does this depends entirely on where it currently is in that sequence. If the core is still in the oxygen-burning stage, we might have centuries. If it has already transitioned to silicon burning, if the iron core is already growing, then we are talking about timelines that are geologically instantaneous. And the frustrating, haunting truth is that we cannot see the core directly. The surface of Betelgeuse is a roiling, convective, violently churning shell of plasma that tells us about surface conditions, not core conditions. We infer the interior from the surface, and that inference has limits. But the surface has been telling us things. The erratic pulsations, the unprecedented dimming, the subsequent overcorrection in brightness. These are not proof of an iron core, but they are consistent with a star whose interior dynamics are changing, which is consistent with a star moving through the later stages of its nuclear fuel sequence. And it is that consistency, more than any single data point, that makes the 4-year window worth taking seriously as a speculative frame. Here is what we know about Betelgeuse's position in the sky and why its death matters to us in ways that go beyond the merely spectacular. The star sits at a distance of approximately 700 light-years. This is close by the standards of things that explode. The nearest supernova in recent astronomical history occurred in 1987 in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, at a distance of roughly 168,000 light-years. Even at that distance, the explosion was visible to the naked eye from the southern hemisphere, the only naked eye supernova since Kepler's star in 1604. Betelgeuse is 240 times closer than the 1987 event. The difference in apparent brightness would be staggering. When Betelgeuse goes supernova, astronomers estimate it will shine somewhere between magnitude -9 and magnitude -12. For context, the full moon sits at around magnitude -13. This means a Betelgeuse supernova could approach or nearly match the brightness of the full moon, not the disk of the moon, but the total light output spread across a single point in the sky. It would be visible during the day, it would cast shadows at night, it would be bright enough to read by, it would be the most dramatic astronomical event witnessed by human beings since at least the supernova of 1006, which was observed and recorded by astronomers across China, Egypt, Iraq, and Europe, and which may have reached a brightness comparable to what Betelgeuse might produce. That event, 1,000 years ago, was from a star roughly 7,000 light-years distant. Betelgeuse is 10 times closer. The light show would last for weeks. Not a flash, not a brief brightening, but a sustained period, potentially several months, during which Orion's shoulder blazes with impossible intensity, visible to every human being on Earth who has access to an unobstructed view of the sky. News coverage would be immediate and total. Every telescope on Earth and in orbit would swing toward it. Every radio telescope, every X-ray observatory, every neutrino detector would light up, because the signal would not come only in light. It would come first, before any photons, before any visible brightening, in the form of neutrinos. This is one of the most remarkable facts about a supernova. The light we see is not the leading edge of the explosion. Neutrinos are. Though at the moment of core collapse, the star releases an almost incomprehensible burst of neutrinos, roughly 10 to the power of 58 of them, carrying away approximately 99% of the total energy of the explosion. These neutrinos, travelling at nearly the speed of light and interacting almost not at all with normal matter, escape the star instantly, while the shock wave is still fighting its way through 700 solar radii of stellar material. By the time that shock wave reaches the surface of the star and the light flash begins, the neutrinos are already gone. They travel outward at essentially the speed of light. The light follows, but the light is delayed by the hours it takes the shock wave to cross the star's diameter, and further delayed by the time it takes the brightness to build the spectacular peak we would observe. What this means, practically, is that the first warning we will have of a Betelgeuse supernova will not be light. It will be neutrinos detected by underground observatories, facilities like Super Kamiokande in Japan, IceCube at the South Pole, and others roughly 1 to 3 hours before the sky changes. There are automated alert systems now in place specifically for this scenario. If a burst of neutrinos consistent with a nearby core collapse is detected, those systems are designed to broadcast an immediate alert to the global astronomical community, giving observatories time to point their instruments at Betelgeuse before the optical brightening begins. We have built an early warning system for this event. That is how seriously the community takes the possibility, even if the public conversation remains cautious. This is where we are at the beginning of our countdown. Somewhere in the shoulder of Orion, a star is burning through its final fuel. Its surface is churning and pulsating in ways that have no clean precedent in the observational record. Its brightness has been behaving erratically for half a decade. Researchers have published models suggesting its terminal event may be nearer than previously assumed, and the instruments designed to catch the first signal of its collapse are running, waiting, pointed at the right patch of sky. We do not know if the 4-year window is correct. We do not know if the window is 10 years or 100 or 10,000, but we know the window exists. We know it is finite, and we know that when it closes, the sky will never look the same again. In the next part of this countdown, we are going to move into the phases that immediately precede a supernova, what the star is doing internally in its final years, months, and weeks. We will walk through the stages of burning, the behavior of the stellar surface, and what signals, if any, might give us advance warning that the moment is approaching. Because one of the most fascinating and unsettling aspects of this entire story is that the explosion, when it comes, may arrive with almost no warning at all, or it may announce itself in ways we are only beginning to learn to read. Either way, the clock is running. The light already travelling toward us from Betelgeuse left that star around the year 1325. Whatever is happening there right now, we will not know about it for 7 centuries. But what is happening there right now, whatever stage the core has reached, whatever balance is being maintained or is about to break, that is the thing that determines whether the 4-year window is real. And that is the thing we cannot see. We can only wait for it to arrive. There is a particular kind of silence that comes with watching something inevitable. Not the silence of emptiness, but the silence of held breath, the pause between the last thing that was and the first thing that will be. Astronomers who study Betelgeuse have been living inside that silence for years now. They go to their data every morning. They pull up the latest photometric readings, the spectroscopic analyses, the interferometric images that map the star's churning surface in extraordinary detail. They look at the numbers. They compare them to yesterday's numbers, last month's numbers, the numbers from before the Great Dimming. And then they write their papers, attend their conferences, give their careful, measured interviews, and somewhere beneath all of that professional composure, they carry the awareness that they might be the generation of astronomers who watches Betelgeuse die. That awareness does not make them reckless with their conclusions. If anything, it makes them more careful. But it is there. It shapes the questions they ask. It determines which data they consider worth chasing. And it is the reason that right now, in the mid-2020s, Betelgeuse is probably the most intensively observed single star in the history of astronomy. To understand what those observations are showing us, what the instruments are picking up, what the models are predicting, and what the next phases of this countdown actually look like, we need to go inside the star. Not literally, of course. We cannot send anything into a red supergiant 700 light-years away, but we can follow the physics. We can trace the sequence of events that stellar evolution theory tells us must be occurring, and we can map those events onto a timeline that gives us a framework for thinking about what comes next. This is what astrophysicists do when they model the final stages of a massive star's life. They take the known physics of nuclear burning, gravity, and thermodynamics. They feed in the initial conditions of the star's mass and composition, and they let the equations run forward in time. The result is a predicted sequence, a script, in a sense, for the star's final act. Betelgeuse has been following some version of that script for millions of years. The question we are asking now is, which page are we on? The sequence begins with what happened long before any human being was alive to observe it. Betelgeuse ignited as a main sequence star somewhere between 8 and 10 million years ago. At that point it was hotter, bluer, and more compact than it is today. A massive O-type star burning hydrogen in its core with the profligate energy budget of something that has no concept of conservation. For millions of years it burned that hydrogen, converting it to helium, releasing energy, maintaining the pressure balance against gravity. Then the hydrogen in the core ran out. The core, now composed primarily of helium, began to contract under gravity. The contraction heated the core until helium fusion ignited, a process called the triple alpha reaction, in which 3 helium nuclei fuse to form carbon. The onset of helium burning caused the outer layers of the star to expand dramatically, and Betelgeuse became what it is today. A red supergiant, bloated and cool at the surface, burning helium in its core while hydrogen continued burning in a shell around it. Helium burning ran for hundreds of thousands of years. Then the helium in the core was exhausted and the sequence advanced again. Carbon burning ignited. Carbon fusion produces a mixture of oxygen, neon, and magnesium, and it runs on a timescale of thousands of years. Then neon burning, which photodisintegrates neon nuclei and rearranges them into oxygen and magnesium. Neon burning runs for roughly a year in a star of Betelgeuse's mass. Then oxygen burning begins, fusing oxygen into silicon, sulfur, and other intermediate elements. Oxygen burning runs for several months to a few years, depending on the star's mass and the specific conditions in its core. And then comes silicon burning, the final stage, the last gasp, the process that builds iron from silicon through a rapid sequence of reactions and runs in a star like Betelgeuse for approximately 1 week before the iron core becomes too massive to support itself and collapses. This sequence is the internal clock of the star's death. And the critical, haunting fact about it is that from the outside, the surface of the star does not change dramatically as the core moves through these stages. The convective outer envelope of Betelgeuse, the vast, roiling shell of plasma that we see when we image the star, is largely decoupled from what is happening in the core. The core might be burning oxygen right now, or silicon, and the surface would look broadly similar either way. We cannot read the stage of core burning directly from surface observations. What we can do is look for indirect signals, changes in pulsation behavior, shifts in convection patterns, variations in the chemical composition of material ejected from the star's atmosphere, and try to infer something about the interior from those indirect measurements. This is where the post-2019 data becomes genuinely interesting and genuinely difficult to interpret cleanly. The disruption of Betelgeuse's primary pulsation cycle, the 420-day oscillation that had been the star's most reliable behavioral signature for over a century of observation, is one of the things researchers cannot fully explain. Pulsation in a red supergiant is driven by the interaction between convection, irradiation pressure, and the opacity of the stellar envelope. When the interior dynamics of a star change, when new burning stages ignite, when the core contracts, when the energy output from the core shifts, those changes can propagate outward and affect surface pulsation. The disruption of the 420-day cycle after the Great Dimming has been proposed by some researchers as potentially reflecting exactly this kind of interior change, not definitively, not with certainty, but consistently enough with that explanation that the proposal has survived peer review and continued discussion. There is also the matter of the convective cells. One of the most striking things about modern observations of Betelgeuse is that we can actually image the surface of this star in enough detail to see its convective features, the enormous, the continent-sized bubbles of hot plasma rising from the interior, releasing energy at the surface and then sinking back down. These cells are vastly larger than anything on our Sun. A single convective cell on Betelgeuse might be larger than the entire orbit of Earth. And in the years since the Great Dimming, the behavior of these cells has been observed to be particularly vigorous. The star's surface convection has appeared unusually active, with large-scale motions detected by interferometric instruments that suggest a turbulent interior. This, again, is not definitive. Red supergiants are inherently turbulent objects. But the degree of activity, its persistence, and its correlation with the other anomalous behaviors combine to paint a picture that is harder to dismiss than any single observation on its own. Then there is the mass loss. All red supergiants lose mass. They shed material from their outer layers continuously, driven by radiation pressure and convection, creating a stellar wind that carries plasma, dust, and gas out into the surrounding space. Betelgeuse has been doing this throughout its life as a red supergiant, and the result is a complex nebular environment surrounding the star, shells and arcs, and clumps of ejected material that trace the history of its mass loss over thousands of years. But the event that preceded the Great Dimming, the surface mass ejection that produced the dust cloud blocking our view, was not routine stellar wind. It was a localized, violent expulsion of a mass of material roughly 2 million kilometers across from the star's southern surface. This kind of surface mass ejection, or SME, had not been observed before in Betelgeuse or any comparable star. Its cause is still debated. One leading hypothesis is that a particularly large convective cell rose to the surface, erupted, and launched material outward with enough velocity to escape the star's gravity. Another hypothesis connects the ejection to the star's internal dynamics, suggesting that changes in the energy output from deeper burning layers might have created pressure waves that propagated outward and triggered the surface event. Whatever its cause, the SME of 2019 left a mark, not just on our observations, which have been tracking the subsequent evolution of that ejected material, but on the star itself. The surface region from which the material was ejected showed anomalous cooling afterward. Teeth, a cold spot that persisted for months and contributed to the continued asymmetric appearance of the star in interferometric images. The star's face, in other words, is still wearing the scar of that event, and some researchers have pointed out that the persistence of that scar, the fact that the affected surface region has not fully recovered to pre-ejection conditions even years later, might indicate that the ejection was not simply a surface-level event, that it may have involved or been driven by changes at greater depth. Let us now construct the timeline of the star's interior in the scenario where the 4-year window is real. If Betelgeuse is to explode within approximately 4 years of now, then its silicon burning phase, which lasts roughly 1 week, would need to begin within the next few years. Silicon burning is preceded by oxygen burning, which runs for months. Oxygen burning is preceded by neon burning, which runs for roughly a year. This means that if the 4-year window has any validity, Betelgeuse is almost certainly already in the oxygen-burning phase, and may have been for some time. It might even be in the late stages of oxygen burning, approaching the transition to silicon. We cannot verify this directly. But we can note that the behavior of the star's surface since 2019 is not inconsistent with a star whose core is undergoing these advanced burning stages that produce higher energy outputs, more violent convective motions, and greater mass loss events than the earlier phases of stellar burning. This is the part of the story that tends to make people feel something complicated, because the physics here describes a sequence that, once begun, cannot be stopped. There is no intervention possible, no mechanism by which a star in the oxygen-burning or silicon-burning stage reverses course. The sequence runs in one direction only, driven by the iron logic of nuclear physics and thermodynamics. Each stage exhausts its fuel and hands the star off to the next stage, with the inevitability of a falling object. The star is not choosing to die. It is simply running out of options, one element at a time, one nuclear threshold at a time, until it reaches iron and finds that there is nothing left to burn and nowhere left to go but down. What would we detect, if anything, in the period immediately before the collapse? This is one of the most important and most uncertain questions in the entire field of supernova astrophysics. My theory suggests that in the final months and years before a core collapse supernova, a massive star might exhibit certain precursor behaviors: elevated mass loss, increased luminosity fluctuations, unusual spectral changes that could, in principle, serve as warnings. The problem is that we have never directly observed these precursors in a star we subsequently watched explode. Every supernova we have detected in the modern era has been discovered after the fact. We see the flash, we identify the host galaxy, and then we search archival images for the progenitor star. We have done this successfully in many cases, including the 1987 supernova, where the progenitor was later identified in pre-explosion images. But we have never sat watching a specific star with all our instruments and seen it transition from living to exploding in real time. Betelgeuse gives us, for the first time in history, a real shot at doing exactly that. It is close enough, bright enough, and thoroughly enough observed that if it produces any detectable precursor signal, we have a genuine chance of catching it. The neutrino burst will come first, as described in the previous section, roughly 1 to 3 hours before the optical brightening. But some models suggest that before even the neutrino burst, there might be a period of elevated surface activity, a brightening or a series of brightness fluctuations as the core transitions through its final burning stages and the energy being deposited into the envelope increases. This pre-explosion brightening, sometimes called a pre-supernova outburst, has been observed in other types of massive stars, particularly a class called luminous blue variables, though its existence in red supergiants is less well established. If Betelgeuse produces such an outburst, our instruments will catch it. The star is monitored continuously. Any anomalous brightening would be flagged immediately. This continuous monitoring is itself a remarkable fact about where we stand. Betelgeuse is not just being watched by professional astronomers, it is being watched by a global network of amateur astronomers who submit brightness measurements to databases like the American Association of Variable Star Observers, which has been collecting data on Betelgeuse for decades. It is being watched by the Solar Mass Ejection Imager and other wide-field cameras that sweep the sky continuously. It is being watched by the Very Large Telescope's gravity instrument, which is capable of imaging the star's surface features at a resolution that would have been science fiction 20 years ago. It is being watched by radio telescopes sensitive to the thermal emission from its surrounding dust shells. And it is being watched at a level most people do not realize by the neutrino detectors, which are not actively watching Betelgeuse specifically, but which would immediately flag any burst of neutrinos arriving from the direction of Orion. We have built, without necessarily framing it this way publicly, a comprehensive early warning system for the death of a specific star. That is extraordinary. That is something no previous generation of human beings could have done or did do. And it speaks to how seriously the people closest to this data take the possibility that the event might happen within a time frame that is relevant to their careers and their lives. Now let us talk about what happens in the hours and days immediately following core collapse, because this is where the countdown stops being about waiting and starts being about witnessing. The core collapses in less than a second to go from a supported iron core to a proto-neutron star of nuclear density. The density achieved in that moment is so extreme that it surpasses the density of an atomic nucleus, matter compressed to the point where individual protons and neutrons are touching, where the physics of everyday experience becomes irrelevant and the strange rules of nuclear and particle physics take over completely. The collapsing outer layers, which were following the core inward, hit this newly formed nuclear object and rebound with a shock wave that carries an energy equivalent to roughly 10 to the power of 44 joules. That number is not usefully comparable to anything in ordinary experience. It is approximately equal to the total energy our Sun will radiate over its entire lifetime, released in a single bouncing shock wave in a matter of seconds. The shock wave propagates outward through the star's layers. As it travels, it heats the surrounding material explosively, triggering additional nuclear reactions and synthesizing heavy elements. Many of the elements that exist on Earth, including the iron in your blood and the calcium in your bones, were created in events like this one. The shock wave takes roughly a few hours to cross the star's diameter and reach the surface. At that point, the surface of the star begins to brighten with extraordinary speed. The initial brightening, called the shock breakout, lasts for only a few minutes to a few hours, a brief pulse of X-ray and ultraviolet radiation as the shock wave punches through the stellar surface. If instruments are watching at the right wavelengths at the right moment, this shock breakout can be directly observed. It has been caught in other supernovae by telescopes like Kepler and the Swift Observatory. For a Betelgeuse explosion, given the density of monitoring we have in place, the probability of catching the shock breakout is extremely high. After the initial shock breakout, the visible brightening continues over the following days and weeks as the expanding shell of ejected material cools, recombines, and releases the energy deposited by the shock wave in the form of visible light. The light curve of a core collapse supernova typically reaches its peak brightness somewhere between 2 and 4 weeks after the initial explosion. This is when Betelgeuse would be at its most spectacular, blazing in the shoulder of Orion at a brightness that would be visible in daylight and that would dominate the night sky for weeks. People who had never looked up before would look up. People who did not know Betelgeuse existed would know it then. It would remain brighter than any star in the sky for several months, slowly fading as the ejected shell expanded and cooled. The fading would follow a characteristic pattern driven by the radioactive decay of elements synthesized in the explosion, primarily nickel-56, which decays to cobalt-56, which decays to iron-56, each step releasing gamma radiation that heats the expanding shell and drives the light curve. Astronomers would measure this decay precisely and use it to constrain the mass of radioactive nickel produced in the explosion, which in turn constrains models of how the explosion occurred and what it left behind. What it leaves behind is one of two things: either a neutron star, an object of nuclear density roughly 20 kilometers across but containing more than a solar mass of material, spinning rapidly and emitting intense radiation as a pulsar, or, if enough mass falls back onto the neutron star after the initial explosion, a black hole. Which outcome occurs depends on the precise mass of Betelgeuse's core at the time of collapse, and on the details of the explosion mechanism. Current estimates suggest that Betelgeuse is most likely to produce a neutron star, though the high-mass end of the estimates for its total mass put it in a regime where a black hole is not impossible. The difference matters for what we observe in the years following the explosion. A neutron star will eventually become detectable as a pulsar, as the 1987 supernova remnant is expected to eventually reveal its compact remnant. A black hole will be invisible. What will definitely be visible for thousands of years is the nebula. The expanding shell of ejected material will light up as it collides with the existing circumstellar material that Betelgeuse has been shedding throughout its red supergiant phase. The collision will create a glowing shock front, a supernova remnant that will slowly expand and cool over millennia, becoming one of the most spectacular nebulae in the sky. Given its proximity, 700 light-years is close enough that a supernova remnant there would eventually span a significant angular area of sky. It will be visible to amateur telescopes for many generations. Long after the initial spectacle fades and Betelgeuse disappears from the constellation Orion, its ghost will remain. A growing, glowing cloud of gas and dust, the dispersed remains of a star that burned for 10 million years and died in a second. Orion itself will be changed. Here, the constellation we know, the distinctive pattern of stars that human beings have been naming and storytelling about for tens of thousands of years, will lose one of its defining members. The bright red star at the upper left shoulder will be gone, replaced, eventually, by a faint, expanding nebula. The constellation that has guided sailors, inspired hunters, marked the seasons and appeared in the myths of cultures on every inhabited continent will look different. Not unrecognizably different, and the belt, the sword, the other bright stars will remain, but Betelgeuse will be missing, and anyone who has learned to find Orion by its reddish shoulder will notice the absence. That absence will persist for the rest of human history, long after the last person who watched the explosion is gone. Long after every record we make of it has been revised and republished and archived, and perhaps lost and rediscovered. The constellation will carry that gap the way a smile carries a missing tooth, still recognizable, still itself, but changed in a way that once you see it, you cannot unsee. We are living in the last period of human history in which Orion looks the way it has always looked. We do not know if that period lasts for more years or 40,000, but it is finite. It is ending. And somewhere in the shoulder of that constellation, the process that will end it is already underway, burning through its final fuel with the calm, patient, absolute certainty of physics that has never been wrong about how this goes. In the next part of our countdown, we are going to move outward, away from the star itself and toward the question of what a Betelgeuse supernova actually does to Earth. Not in the catastrophic, extinction-level way that the worst-case scenarios sometimes suggest, but in the real, measured, scientifically grounded way that the evidence supports. Because this event will not destroy us, but it will reach us. The radiation will reach us. The cosmic rays will reach us. The neutrinos will reach us. And in ways both tangible and subtle, the universe after this explosion will be slightly, measurably, permanently different from the universe before it. We will walk through all of it. The effects on the atmosphere, on the biosphere, on our technology, Torm, and on the longer timescales of what the remnant does to the space around our solar system over the centuries and millennia that follow. There is a question that arrives almost without fail whenever a conversation about Betelgeuse reaches a certain depth. It arrives in the comments of astronomy videos, in the questions asked after public lectures, in the messages sent to researchers by people who have just learned about this star for the first time, and are lying awake at night, turning the information over in their minds. The question is simple, And it is the right question to ask. It is the question that every human nervous system, wired by millions of years of evolution to assess threats and calculate survival odds, eventually arrives at when confronted with the information that something enormous is about to explode relatively nearby. The question is, are we safe? The answer is yes, but the answer is yes in a way that requires some unpacking, because yes does not mean untouched, yes does not mean irrelevant, yes does not mean that the explosion of Betelgeuse will pass through our corner of the solar system without leaving any mark whatsoever. What it means is that the event will not kill us. It will not trigger a mass extinction. It will not strip our atmosphere, sterilize our oceans, or end the project of complex life on this planet. The threshold distance for a supernova to pose an existential threat to Earth is estimated by most researchers to be somewhere around 25 to 50 light years. Some more conservative estimates extend that danger zone to perhaps 100 light years. Betelgeuse is approximately 700 light years away. We are well outside the kill zone by any reasonable definition of that term, but well outside the kill zone is not the same as completely unaffected. And the ways in which we will be affected, some immediate, some unfolding over decades and centuries, are worth understanding clearly because they are part of what makes this event genuinely significant rather than merely spectacular. Let us start with the thing that arrives first. Not light, as we have established, but neutrinos. The neutrino burst from a Betelgeuse supernova will reach Earth before any other signal. Approximately 10 to the power of 58 neutrinos will be produced in the core collapse, carrying away roughly 99% of the total energy released. These particles travel at essentially the speed of light, interacting so weakly with matter that they pass through the entire mass of the Earth as if it were not there. Every square centimetre of Earth's surface will be crossed by billions of these neutrinos in the seconds during which the burst passes. Your body will be traversed by them. You will not feel it. You will not be harmed by it. Neutrinos are among the most ghostly particles in existence. They can pass through a light year of solid lead with only a 50% chance of interaction. A few seconds of neutrino flux from a nearby supernova will not harm a single cell in your body, but the neutrino detectors will scream. Super Kamiokande, the 50,000-ton tank of ultra-pure water buried deep beneath a Japanese mountain, is designed to catch the rare interactions when a neutrino does collide with a water molecule. Under normal circumstances, it detects a handful of neutrinos per day from various sources. During the neutrino burst from a Betelgeuse supernova, it would detect somewhere in the range of 5,000 to 10,000 neutrino events in approximately 10 seconds. IceCube at the South Pole, with its cubic kilometre of instrumented Antarctic ice, would see a similar flood. Every neutrino observatory on the planet would register the signals simultaneously, and automated alert systems would immediately broadcast the news. Core collapse in progress. Direction of Orion. All instruments orient now. This early warning, arriving 1 to 3 hours before the visible brightening, would be the most significant astronomical alert ever transmitted. Every telescope, every satellite, every observatory on Earth and in space would be redirected within minutes. The light arrives next. Gamma rays and X-rays from the shock breakout will come first, at the speed of light, followed by the rapid brightening in ultraviolet, and then visible wavelengths as the explosion unfolds. The gamma-ray flux from a Betelgeuse supernova reaching Earth will be detectable by our space-based gamma-ray observatories, but it will not be dangerous. At 700 light-years, the gamma-ray fluence, the total energy deposited per unit area, falls well below the levels that would cause significant effects on Earth's atmosphere or biosphere. The dangerous gamma-ray scenarios involve much closer events, or the highly collimated gamma-ray jets, produced by a specific and relatively rare type of supernova called a long-duration gamma-ray burst, which Betelgeuse is not expected to produce. Betelgeuse will explode as a standard core collapse supernova, releasing its energy roughly isotropically, in all directions rather than in focused jets. The gamma-ray flux we receive will be measurable and scientifically fascinating, but not threatening. The visible light, as described previously, will be extraordinary. Peak brightness somewhere between the brightness of the quarter moon and the full moon, sustained over weeks, gradually fading over months. For the duration of the peak, this will be the dominant astronomical object in the sky after the sun and moon. It will be bright enough to disrupt the night-adapted vision of any animal that uses visual cues at night. It will be bright enough to interfere with astronomical observations of other targets. For a period of weeks to months, any telescope pointed anywhere near Orion will have to account for the overwhelming nearby source. It will be bright enough that light pollution concerns, usually the domain of ground-based astronomers complaining about city lights, will be temporarily superseded by a natural source so bright it creates its own version of the problem. There will be practical effects on Earth's surface that go beyond the visual. The ultraviolet component of the explosion's light output may cause a measurable but modest increase in UV flux, reaching Earth's surface. Current estimates suggest this increase would be well within the range of natural variation, similar to the difference in UV exposure between cloudy and clear days, or between equatorial and polar latitudes. It will not cause a surge in skin cancer rates, will not damage crop yields, and will not harm ecosystems in any meaningful way. The ozone layer, which protects Earth's surface from UV radiation, will absorb the additional flux without significant depletion. Some models suggest a very slight, temporary reduction in stratospheric ozone from the combined effects of UV and the later arriving cosmic rays, but the magnitude of this effect is expected to be small and transient. Cosmic rays are the second major physical effect to consider, and they arrive on a very different timescale from everything else. When the supernova shockwave expands into the surrounding interstellar medium, it accelerates charged particles, protons, electrons, and heavier atomic nuclei to extremely high energies. These are cosmic rays, the high-energy particles that constantly rain down on Earth from all directions, products of violent events throughout the galaxy. A nearby supernova is one of the primary sources of galactic cosmic rays, and a Betelgeuse explosion will produce a significant burst of them. But unlike light, which travels at a fixed velocity and arrives in a coherent pulse, cosmic rays are charged particles that interact with magnetic fields in the interstellar medium. They do not travel in straight lines. They spiral and scatter, following complex paths that spread their arrival out over time. The cosmic ray enhancement from a Betelgeuse supernova will not arrive for decades to centuries after the light does, and when it does arrive, it will be spread over a similarly long time scale. The increase in cosmic ray flux reaching Earth may be detectable above the background level for centuries. This is actually one of the more scientifically significant long-term effects of the event. Cosmic rays have measurable consequences for Earth's atmosphere and potentially for its climate. They ionize air molecules in the upper atmosphere, a process that may influence cloud nucleation, the formation of cloud droplets around ionized particles. The connection between cosmic ray flux and cloud cover, and through cloud cover and climate, is an active area of research with genuine uncertainties. Some studies have proposed that periods of elevated cosmic ray flux in Earth's geological past, potentially related to nearby supernova events, may have correlated with periods of climate variation. Whether a Betelgeuse supernova would produce a large enough and sustained enough increase in cosmic ray flux to drive detectable climate effects is uncertain, but it is not a question that can be dismissed. The honest answer is that we do not know precisely, and that monitoring the cosmic ray environment in the decades following the explosion will be one of the most scientifically valuable ongoing measurements available to researchers. At the biological level, the direct effects of the event on Earth's life should be minimal. The radiation levels will not cause measurable increases in mutation rates. The UV enhancement will not significantly stress ecosystems adapted to far larger natural variations in UV exposure. The cosmic ray enhancement, arriving gradually over decades, will be too diffuse to cause acute biological effects. However, there is one category of organism that may experience noticeable disruption in the immediate aftermath of the optical brightening, and that is the category that navigates, feeds, reproduces, or communicates using the darkness of the night sky as a reference. Many species of nocturnal animals, insects, birds, marine organisms, amphibians, have behavioral systems calibrated to natural light levels. The sustained brightness of a Betelgeuse supernova, particularly during its peak weeks, represents a level of artificial night illumination, comparable to the full moon maintained continuously, rather than cyclically. Species that time their reproduction to lunar cycles that use star patterns for navigation or that rely on darkness for predator avoidance may experience disruption on the scale of weeks to months. This is not an extinction-level concern, but it is a genuine ecological effect. And it is the kind of effect that serves as a reminder that the boundary between the cosmic and the biological is more permeable than we usually think. The universe has always been reaching into the biosphere, shaping evolution through radiation events, climate perturbations, and impact events. A Betelgeuse supernova is another such reaching, smaller and gentler than the worst of what has happened before, but real, measurable, and part of the ongoing conversation between the cosmos and the living planet. Now, let us talk about our technology. We live in a civilization that is significantly more dependent on electronic and satellite infrastructure than any previous civilization, and that infrastructure has variable sensitivity to radiation events. The immediate radiation from the supernova, the gamma rays, X-rays, and optical light will not pose a direct threat to satellites or electronic systems. The intensities involved are too low at 700 light-years to damage shielded electronics or disrupt satellite operations. However, there is a subtler consideration involving the ionospheric effects of elevated UV and X-ray flux. Earth's ionosphere, the electrically charged upper atmosphere layer that reflects and absorbs radio waves, is sensitive to changes in solar X-ray and UV output. As anyone who tracks radio propagation for amateur radio or communications purposes knows, a sudden increase in ionizing radiation from an external source could temporarily alter ionospheric conditions, potentially affecting certain radio communications and navigation systems that rely on ionospheric propagation. The effect would likely be brief, comparable to a moderate solar flare, and would not cause lasting damage to any systems. But It is another example of how the event, while not dangerous, is not entirely without consequence for the civilization it illuminates. The psychological and cultural effects are harder to quantify, but perhaps equally significant in a human sense. Consider what it means for billions of people to look up and see something in the sky that was not there before, something bright enough to be undeniable, spectacular enough to demand attention, impossible to mistake for anything other than what it is. Consider that this would happen in an era of instantaneous global communication, of live-streamed reality, of social media that can carry an image or a piece of information to 1 billion people within hours. The cultural moment of a Betelgeuse supernova would be unlike anything in modern history. It would combine the universality of a natural event, visible to every human being on the planet, with access to the sky, with the capacity for instant collective experience that only exists in the age of digital communication. Every major religion would respond, every philosophy concerned with the scale and meaning of human existence would find itself suddenly in conversation with an event that makes that scale viscerally apparent. Or the night sky would become, for weeks, something that people who had never thought about it before would stand outside and contemplate. The question of what it means, of whether it is a sign of what it says about the universe and our place in it, these questions would enter the mainstream in a way that no astronomical event has managed in the modern era. The 1997 Hale-Bopp comet was visible for months and generated widespread public interest. The 2017 total solar eclipse produced a moment of collective awe across North America. A Betelgeuse supernova would be both of those things simultaneously, sustained over months, visible from every continent, and carrying the additional weight of knowing that something that has existed since before human civilization has permanently ended. Artists would respond. Writers, composers, painters, the filmmakers. The creative response to a sustained, undeniable astronomical spectacle visible to all of humanity simultaneously would be one of the most significant cultural events in modern art history. The supernova would enter the symbolic vocabulary of every culture on Earth. It would be named, painted, composed about, written into stories, incorporated into religious iconography, referenced in political speeches, used as a marker of before and after, in the way that only a handful of events in human history have managed to achieve. The sky itself would carry the record of it. First the blazing point of light, then the slowly fading remnant, then the glowing nebula expanding through the centuries, always visible in the constellation that will never again look quite like what our ancestors drew. For astronomers, the event would be the scientific opportunity of multiple lifetimes. The data collected in the first hours, days, and weeks would occupy researchers for generations. The neutrino signal alone would provide the most detailed look at a core collapse event ever achieved, potentially resolving long-standing debates about the exact mechanism of supernova explosion, the formation of neutron stars, and the behavior of nuclear matter at extreme densities. The shock breakout signal, if caught in multiple wavelengths, would test and refine models that have been built on far more distant and poorly resolved events. The chemical composition of the ejected material, measured spectroscopically as the explosion brightens and evolves, would provide a direct window into the nucleosynthesis occurring in the explosion, the forging of heavy elements that will eventually be incorporated into future star systems, future planets, and perhaps future life. The neutrino data in particular could be transformative. One of the unresolved questions in supernova physics is exactly how the shock wave that causes the explosion is revived and sustained after it initially stalls in the dense inner regions of the collapsing star. Theory suggests that neutrinos play a crucial role, that the sheer flux of neutrinos streaming outward from the proto-neutron star deposits enough energy in the stalled shockwave to restart it and drive the explosion. But the details of this neutrino-driven explosion mechanism are not fully worked out, and the models have uncertainties that can only be resolved by detailed observational data from a nearby event. A Betelgeuse supernova would provide that data in extraordinary volume. The neutrino detectors would record not just the bulk flux, but the time structure, energy distribution, and flavor composition of the burst, information that maps directly onto the conditions in the collapsing core during the first seconds after bounce, which are the seconds that determine whether the star explodes successfully or collapses directly into a black hole. There is also the question of what comes next in the direction of Betelgeuse, not for us, but for the space around the explosion. The expanding shockwave from a supernova does not simply disperse into nothingness. It sweeps up interstellar gas and dust as it expands, compressing it into a shell that can trigger the formation of new stars. This is one of the mechanisms by which supernovae contribute to the ongoing cycle of stellar birth and death in galaxies. By compressing nearby molecular clouds enough to trigger gravitational collapse, they seed the next generation of stars. The region of space around Betelgeuse, which is part of a larger complex of young stars and gas called the Orion OB1 Association, contains enough raw material that the shockwave from a Betelgeuse explosion could, over the time scale of millions of years, contribute to the formation of new stellar systems in the region. The star's death, in other words, is not simply an ending. It is a contribution to a process that has been running since the galaxy formed. The recycling of stellar material into new generations of stars, some of which will eventually host planets, some of which will eventually host whatever comes next in the universe's long experiment with complexity. The iron and other heavy elements forged in the explosion and scattered into the interstellar medium will be incorporated into future star systems that form from that material. The iron in those future systems, in their rocky planets, in whatever minerals and biology might eventually arise there, will carry the atomic signature of Betelgeuse's death. This is not a poetic metaphor. This is literally how heavy elements are distributed through the galaxy. The iron in your blood was made in a supernova, some specific supernova billions of years ago, whose name we do not know and whose light we will never see. Yes, Betelgeuse will make a contribution of exactly this kind to the future. Its death will seed the galaxy with material that will eventually end up in places we cannot predict, doing things that the laws of chemistry and physics and biology will determine. The star ends, the atoms continue, and on Earth the night sky will continue as well, changed but continuing. The long fading of the supernova remnant will take place over months and years. The glowing shell, the expanding nebula, will become a fixture of the constellation Orion for centuries. Amateur astronomers 100 years from now will be able to point small telescopes at the remnant and see it still growing, still glowing, still carrying the energy of the explosion outward into the surrounding medium. 1,000 years from now, it will have expanded to cover a significant angular area of sky, rivaling or exceeding the angular size of the largest known supernova remnants visible from Earth. It will be one of the treasures of the night sky for the rest of human history, assuming human history continues long enough to witness it. That assumption is one we should not take for granted. And this is where the story of Betelgeuse connects to the larger story that this channel exists to tell. The story of time, of countdown, of the cosmic clock that measures everything against everything else and finds that all of it is temporary, all of it is phase, all of it is stage, in a sequence that was set in motion at the beginning and will run until the end. Betelgeuse is dying on a schedule it did not choose, following physics it cannot escape. And Earth is moving through its own sequence, its own set of phases and stages and countdowns, with the same inexorable physics driving it forward. The supernova is one event in a universe full of events, each with its own timeline, each with its own countdown, each arriving on a schedule that is indifferent to our presence and our preferences. But we are here for it. We are here with our instruments and our theories and our neutrino detectors and our interferometers and our 10,000-year history of looking at the night sky and trying to understand what we are seeing. We are here to watch, to measure, to record, and to think about what it means. No previous generation of human beings had the tools to do this. No previous generation knew what a supernova was, what caused it, what it would do to the space around it, what it would leave behind. We know, imperfectly, incompletely, with margins of error stacked upon margins of error, but we know. And that knowing is not nothing. That knowing is, in the long view, one of the most remarkable things that has ever happened in this corner of the universe. In the next part of our countdown, we are going to zoom out further still. We are going to look at the deeper timeline, what the universe looks like after Betelgeuse, what the Milky Way looks like after Betelgeuse, what the long arc of cosmic time does with the remnant of this explosion and with everything else that is moving on its own countdown toward its own inevitable end. We are going to look at the next stars in our galactic neighborhood that are approaching their own terminal events. And we are going to ask what the night sky of the far future, decades, centuries, millennia from now, will actually look like. Because Betelgeuse is not alone in its dying. The galaxy is full of massive stars in various stages of their terminal sequences, each one a clock, each one a countdown, and the night sky we see tonight is a snapshot of a process that has been running since the first stars ignited and will continue long after the last one goes dark. Zoom out, not just from Betelgeuse, not just from the Orion constellation, not just from the Milky Way, but from the very concept of a single event and a single countdown. Because one of the things that the story of Betelgeuse reveals, when you follow it far enough, is that it is not an isolated story. It is one thread in a tapestry that has been weaving itself since the universe was young. A tapestry made entirely of timelines, of countdowns, of beginnings and endings stacked so densely that every point in space and time is simultaneously the ending of something and the beginning of something else. Betelgeuse is dying, but Betelgeuse is not the only thing dying. The galaxy around it is full of massive stars in their own late stages, following their own sequences, running their own internal clocks toward their own inevitable conclusions. And beyond those stars, beyond the galaxy, the universe itself is running a countdown of such staggering length that the death of Betelgeuse, spectacular as it is, significant as it is, registers as barely a tick on the largest clock we know how to describe. To understand where we are in the largest possible picture, we need to understand something about the structure of cosmic time, the way astrophysicists think about the future of the universe, not in years or centuries, or even millions of years, but in orders of magnitude, in phases so vast that individual stellar lifetimes become invisible within them. The framework that makes this most accessible is the one developed by astrophysicists Fred Adams and Greg Laughlin in their 1999 book on the deep future of the cosmos, a framework that divides the history and future of the universe into 5 broad eras defined by the dominant physical processes operating within each one. We are currently living in what Adams and Laughlin called the stelliferous era, the age of stars. This era began roughly 100 million years after the Big Bang, when the first stars ignited, and it will end in approximately 100 trillion years when the last star capable of sustained fusion burns out. 100 trillion years. Written out, that is a 1 followed by 14 zeros. Our universe is currently about 13.8 billion years old, which means we are roughly 0.014% of the way through the stelliferous era. We are not even in the first chapter of this age. We are in the preface, the overwhelming majority of the time during which stars will exist in this universe has not yet occurred. Betelgeuse's death, in this context, is one of the earlier events in a story that has barely begun. But within the stelliferous era, the distribution of stellar activity is not uniform. The universe was more active in its youth, more star formation, more massive, short-lived stars, more supernovae per unit time, and it is gradually becoming quieter. The rate of star formation across the universe peaked somewhere around 10 billion years ago and has been declining ever since. The universe is, in a very real sense, past its most productive period of stellar creation. New stars are still forming, including right now in the Orion molecular cloud complex that surrounds the constellation in which Betelgeuse burns. But the grand burst of cosmic creativity that populated the universe with its current stellar census is behind us. What lies ahead, on the timescale of tens of trillions of years, is a gradual dimming, a slow decrease in the number of active stars as existing ones die, and the supply of raw material for new star formation is progressively exhausted. This gradual dimming is the backdrop against which everything we are about to discuss takes place. It is the slowest possible version of the countdown that defines this channel. Not a 4-year window or a million-year window, but a 100 trillion-year window, at the end of which the last red dwarf star will finally exhaust its hydrogen fuel and fade into a cold, dark cinder. Between now and then, the universe will witness an enormous number of events: supernovae, galaxy mergers, the slow decay of planetary orbits, the gradual inspiral of stars toward galactic centers, the evaporation of star clusters, the cooling of white dwarfs, and at the very end, when the last fusion fires go out, a universe that was once blazing with 100 billion galaxies, each containing hundreds of billions of stars, will be dark and cold and nearly empty, being populated only by the remnants of what was: black holes, neutron stars, white dwarfs cooling toward absolute zero, and the diffuse fog of particles that was once interstellar gas and cosmic rays. We are nowhere near that ending, but understanding it changes how you think about the events in between, including the one we have been counting down to throughout this video. Betelgeuse's death is not a tragedy in the cosmic sense. It is a recycling event. The material it disperses will eventually become part of new star systems, new planets, new chemistry. The iron and nickel and oxygen and carbon it forges and scatters will spend billions of years drifting through the interstellar medium before being swept up by the gravity of a forming star and incorporated into the disk of gas and dust from which planets grow. And the heavy elements now locked inside Betelgeuse Elements that would never have existed without the star's long life and violent death are about to be liberated into the galaxy, made available for the next round of construction. This is how the universe builds complexity, not in one step, but in iterations, each generation of stars enriching the interstellar medium with heavier elements, each new generation of stars and planets forming from that enriched material, each cycle producing a slightly more complex chemical inventory from which more complex structures can potentially arise. Our solar system is itself a product of this process. The Sun is a third-generation star, formed from material that was processed through at least 2 previous stellar generations. The heavy elements that make up Earth, the iron core, the silicate mantle, the carbon-based chemistry of every living thing, were forged in the cores and explosive deaths of stars that lived and died billions of years before our Sun ignited. We are, in the most literal possible sense, the ash of dead stars. Betelgeuse's ash will eventually become something too. We cannot know what, but the same physics that produced us from the remnants of unnamed ancient supernovae will work on Betelgeuse's remnants with equal patience and equal creativity. Now, let us look at the galactic neighborhood, at the other massive stars in our region of the Milky Way that are approaching their own terminal events, the other countdowns running alongside Betelgeuse's. Because the night sky is not static. The stars we see tonight are not the stars that future generations will see. The gallery of bright objects in our sky is a temporary exhibition, and it is slowly changing, some stars brightening as they age, others fading, others destined to explode within astronomically near timescales. The most prominent candidate after Betelgeuse is Eta Carinae, a massive stellar system roughly 7,500 light-years away in the southern constellation Carina. Eta Carinae is extraordinary even by the standards of extreme stars. It is a binary system containing at least one star with a mass estimated at between 100 and 150 times the mass of our Sun, among the most massive stars known in the galaxy. It is so luminous that it exceeds the theoretical Eddington limit, the maximum luminosity at which radiation pressure does not blow the star apart, which means it is quite literally too bright to be stable. In 1843, it produced a massive eruption called the Great Eruption, that temporarily made it the second brightest star in the sky despite being 7,500 light-years away. The material ejected in that eruption forms the homunculus nebula, a bipolar cloud of gas and dust visible around the star today. Eta Carinae is expected to explode as a hypernova or supernova within a relatively short astronomical timescale. Estimates range from tens of thousands of years to potentially much sooner, and some researchers have speculated that it may already be in a pre-supernova state. At 7,500 light-years, it is far enough away that its explosion will not pose a direct threat to Earth, but it will be spectacular, likely significantly brighter than a Betelgeuse supernova from our vantage point. Depending on whether it produces focused gamma-ray jets aimed in our direction. Closer to home, the star Spica in the constellation Virgo, a brilliant blue-white star about 250 light-years away, is a massive binary system that will eventually produce supernovae, though on timescales of millions of years rather than anything approaching human time. Rigel, the bright blue supergiant at the foot of Orion, roughly 860 light-years away, is another massive star that will eventually explode, though it is estimated to have a longer remaining lifespan than Betelgeuse. The cluster of massive young stars in the Orion OB1 association, the same region that contains Betelgeuse, has already produced multiple supernovae in the past few million years, events whose remnants are still detectable as expanding shells of gas in the region. Betelgeuse itself may have been formed from material enriched by those earlier explosions. Within the next million years, a time frame that is long by human standards but brief by galactic standards, the Milky Way will witness dozens to hundreds of supernovae. The rate of supernovae in our galaxy is estimated at roughly 1 to 3 per century, though this is an average with large uncertainties. On that statistical basis, there may be 1 or 2 supernovae occurring in the Milky Way right now, hidden from our view by the intervening dust of the galactic disk. We will never see most of the supernovae that occur in our own galaxy. The galaxy is too big, too dusty, too opaque in visible light for us to observe events on the far side. We see them instead in radio waves, X-rays, main and gamma rays, wavelengths that penetrate the dust more effectively. The galactic supernova remnant census built up from radio and X-ray surveys reveals hundreds of remnants from past explosions scattered throughout the Milky Way, a record of violence and creativity accumulated over billions of years. The next truly nearby supernova, the next one closer than a few hundred light-years, is harder to predict because proximity is rarer and the candidates less obvious. There are no known massive stars within the truly dangerous zone of 25 to 50 light-years. The Sun's immediate neighborhood is populated primarily by small, dim, long-lived red dwarf stars that will never explode. The nearest star system, Alpha Centauri at 4.37 light-years, contains 2 Sun-like stars and a red dwarf, none of which are candidates for supernova. The nearest genuinely massive star candidates are all at distances comparable to or greater than Betelgeuse. Earth appears to be, at least for the current era, well positioned within the galaxy, far enough from the dense, supernova-rich central regions, far enough from the most massive and volatile star-forming regions, in a relatively quiet suburban neighborhood of the galactic disk. This positional luck is not accidental in the sense that it may be related to why complex life developed here. The galactic habitable zone hypothesis proposes that there is a range of galactic radii, neither too close to the supernova-rich center nor too far from the metal-enriched inner regions, within which the conditions for complex life are most favorable. Our solar system sits comfortably within this proposed zone. The frequency of nearby supernovae over Earth's history has been low enough not to have caused mass extinctions attributable to radiation events, though some researchers have proposed connections between supernova events and certain ancient extinction episodes in the geological record. The evidence for these connections is suggestive rather than conclusive, but it reinforces the point that the boundary between cosmic events and biological history is not as clear as we might prefer. Now, let us move further out in time, past the death of Betelgeuse, past the next few supernovae in our galactic neighborhood, past the million-year and billion-year marks, into the deep future, where the countdowns become almost incomprehensibly long, but no less real. Because this is where the story of cosmic time becomes genuinely strange, where the physics we take for granted in everyday experience gives way to processes so slow they have never been observed directly, where the universe reveals aspects of itself that exist on timescales beyond any biological intuition. In approximately 5 billion years, our Sun will exhaust its hydrogen fuel and begin its transition to a red giant. This is the countdown that most directly concerns the long-term future of Earth and humanity, the countdown that ends with the Sun expanding to engulf, or at least sterilize, the inner solar system. Before that terminal expansion around 1 to 2 billion years from now, the Sun's gradually increasing luminosity will have pushed Earth's surface temperature above the point where liquid water can exist in the open atmosphere, initiating a runaway greenhouse process that will render the planet uninhabitable for life as we know it. The window for complex life on Earth, already more than 4 billion years old, has perhaps another billion to 2 billion years remaining. In the timescales we have been discussing, that is not trivial, but it is finite, and it is among the most important countdowns of all. The Sun's death, when it comes, will be quiet compared to Betelgeuse's. No supernova, no shockwave, no heavy element dispersal. The Sun will expand into a red giant, possibly engulfing Mercury and Venus and scorching Earth beyond recognition, then shed its outer layers in a planetary nebula and leave behind a white dwarf, a cooling, fading ember, roughly the size of Earth, containing most of the Sun's original mass. This white dwarf will cool for billions of years, eventually becoming a black dwarf, a cold, dark, inert lump of carbon and oxygen drifting through space. The time scale for a white dwarf to cool to background temperature is estimated at longer than the current age of the universe, which means no true black dwarfs exist yet. The universe is not old enough to have produced them. They are a feature of a future so distant that it exists outside any framework of human imagination, populated by objects that have not yet had time to form. Beyond the death of the Sun, the galaxy itself continues its evolution. The Milky Way is currently on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor, located approximately 2.5 million light-years away and approaching at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will begin their merger, a process that will unfold over billions of years as the two galactic structures interpenetrate, distort, and eventually merge into a single large elliptical galaxy that astronomers have already nicknamed Milkomeda. This merger will not be the catastrophic collision that the word suggests. Galaxies are mostly empty space, and the stars within them are so widely separated that direct stellar collisions will be extremely rare. But the gravitational dynamics of the merger will dramatically reshape the orbits of billions of stars, potentially disrupting the Sun's current stable orbit around the galactic center and sending it on a new trajectory through the merged galaxy. The effect on Earth of the galactic merger is uncertain in its specifics, but bounded in its severity. The increased stellar density in certain regions of the merging galaxies may elevate the rate of nearby supernova events and the flux of cosmic rays. The disruption of molecular clouds by tidal forces may trigger bursts of star formation. But the solar system, as a gravitationally bound unit, will survive the merger intact. The Sun and its planets will be flung into a new orbit within the merged galaxy, but the internal structure of the solar system will not be disrupted. Earth will continue to exist, though by that point it will long since have been rendered uninhabitable by the Sun's increasing luminosity. After the merger, in the time scales beyond billions of years, the universe enters a phase of genuine quieting. Stars continue to die without being fully replaced. The supply of cold gas available for star formation is progressively exhausted. The most massive stars die quickly, leaving neutron stars and black holes. The intermediate stars die more slowly, leaving white dwarfs. The small red dwarfs, the most numerous and most long-lived stars in the galaxy, persist for tens to hundreds of billions of years, burning their hydrogen so frugally that they outlast everything else by enormous margins. The last red dwarf stars will burn for approximately 10 trillion years. When the last one finally exhausts its fuel and fades, the stelliferous era will be over. What remains? The neutron stars, the white dwarfs cooling toward black dwarfs, the black holes, will be all that persists into the next era. The era that follows, the degenerate era, runs from approximately 100 trillion years to roughly 10 to the power of 40 years. During this period, the dominant objects in the universe are the remnants of stars, white dwarfs, neutron stars, and brown dwarfs. The universe is dark, lit only by the faint glow of cooling stellar remnants and the occasional brief brightening when two white dwarfs collide and produce a Type 1a supernova, the last supernova the universe will ever witness. These late epoch Type 1a events are solitary flashes in a dark cosmos, brief reminders of the violence that characterized the stelliferous era, occurring with ever-decreasing frequency as the population of white dwarfs disperses into the expanding darkness. During the degenerate era, a process called proton decay, if it occurs, and current physics suggests it should, though it has never been directly observed, will gradually disintegrate ordinary matter. Protons, which are the fundamental building blocks of atomic nuclei, are predicted by certain extensions of the standard model of particle physics to be unstable on timescales of approximately 10 to the power of 34 years. If this is correct, then over the time span of the degenerate era, every white dwarf, every neutron star, every brown dwarf, every object composed of ordinary matter will gradually dissolve into lighter particles through proton decay. The solid remnants of a universe full of stars will evaporate, particle by particle, over timescales that make the current age of the universe look instantaneous by comparison. What survives the degenerate era is the black hole era. A universe populated primarily by black holes of various masses, from the stellar mass black holes left by individual supernovae to the supermassive black holes at the centers of what were once galaxies. Black holes do not decay through proton decay because they do not contain protons in the conventional sense. They are not made of ordinary matter, but are instead regions of space-time where the density of matter exceeded all possible support mechanisms. They persist through the degenerate era essentially unchanged, slowly accreting whatever stray particles drift into their gravitational influence. The universe of the black hole era is extraordinarily dark, cold, and sparse. A handful of massive gravitational objects separated by distances so vast that any interaction between them is rare beyond ordinary description. But black holes are not permanent either. Stephen Hawking demonstrated theoretically in 1974 that black holes emit thermal radiation, now called Hawking radiation, as a consequence of quantum mechanical effects at the event horizon. This radiation carries energy away from the black hole, causing it to slowly lose mass. The rate of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes evaporate faster. A stellar mass black hole will evaporate in approximately 10 to the power of 67 years. A supermassive black hole with billions of solar masses will take approximately 10 to the power of 100 years to evaporate. These are the longest countdowns in the universe. These are the last events. the final ticking of the cosmic clock before the last black holes flash out of existence in a burst of high-energy radiation and leave behind nothing but a diffuse soup of fundamental particles in a universe that has reached its maximum entropy, the heat death. The heat death of the universe is the state in which all energy has been evenly distributed, all gradients have been eliminated, and no further work can be extracted from any physical process. It is not an explosion or a collapse. It is a whisper, a gradual, thermodynamically inevitable flattening into perfect uniformity. The universe will not end with a bang. It will end with the last quantum of energy finding its equilibrium, the last fluctuation settling into stillness, the last possible event occurring, and leaving behind a void that will persist, unchanging forever. From the perspective of that ultimate stillness, the death of Betelgeuse is an event of vanishing smallness, a single supernova in a single galaxy during a single century of a universe that will run for 10 to the power of 100 years. A spark in an era of sparks during the brief, brilliant, violent youth of a cosmos that has most of its future still ahead of it. And yet, and this is the thing that matters, it is the spark that we are here to witness. We are the awareness that this process has generated, the point in the universe at which matter has organized itself into something capable of watching, measuring, and understanding what is happening. We are 10 million years of stellar evolution standing in a field on a clear night, looking up at a reddish star in the shoulder of Orion, knowing its name, knowing its age, knowing its internal structure, knowing what it is doing in its core right now, even though we cannot see it, knowing what it will do when it ends, knowing how long that ending will last and what it will leave behind. That is not nothing. In the long accounting of cosmic time, that is actually extraordinary. The countdown to Betelgeuse's supernova is one countdown nested inside a hierarchy of countdowns, the star's internal burning sequence, the star's life within the galaxy's stellar census, the galaxy's life within the universe's stelliferous era, the universe's progression through its 5 great eras toward the silence of maximum entropy. Every scale is real. Every timeline is running simultaneously. And we exist at a particular moment within all of them, a moment early enough in cosmic history that the stars still burn, late enough in stellar evolution that the elements exist to build planets, and chemistry and biology and consciousness, positioned close enough to a dying star to witness its end in spectacular detail. In the final part of our countdown, we are going to bring all of this back to the human scale. We are going to ask what it actually means to be alive during the countdown to Betelgeuse's supernova, what this event asks of us, what it gives us, what it changes about how we think about the night sky and our place within it. We are going to walk through the final phase of our speculative 4-year window, the months, weeks, and days immediately before the explosion, on if the explosion comes, and we are going to sit with the weight of what it would mean to know, in real time, that the sky is about to change forever. Because that is ultimately what this channel is about, not just the physics, not just the timelines, not just the numbers, but what it feels like to be a conscious creature inside a universe that is always, on every scale, counting down to something. There is a moment that astronomers who study variable stars sometimes describe, a moment that comes not in the observatory, not in front of the data, not during the careful measured work of analysis and peer review, but outside, alone, on a clear night, looking up with nothing more than their own eyes at the star they have spent their career watching. The instruments are inside, the models are running on servers somewhere, and the papers are submitted or under review or sitting in a folder waiting to be finished. And they are outside, standing in the cold, looking at a reddish point of light in the shoulder of Orion, and they are thinking, it could be tonight. Not because the data says tonight specifically, not because any model has converged on tonight as the answer, but because the data says soon, in the way that soon means something different when you have been looking at the numbers long enough to feel their weight. And tonight is inside soon. Tonight is always inside soon, once you have accepted that soon is real. This is the emotional texture of the final phase of our countdown, not the sharp urgency of an alarm going off, not the dramatic clarity of a confirmed prediction, but the sustained, ambient awareness that something is approaching, that the ordinary night sky, the one you have known your entire life, the one that was there before you were born and that you assumed would be there long after, is running out of ordinary nights. That awareness is the gift and the burden of living in this particular moment of astronomical history. Previous generations of human beings looked at Betelgeuse without knowing what it was. They named it. They incorporated it into their stories. They navigated by it. They used its reddish color to mark the seasons. But they did not know that it was dying. They did not know what dying meant for a star. They did not know that the light reaching their eyes had left the star hundreds of years before, that they were seeing the past. That the star they were watching was not the star that existed at that moment, but the star that had existed when their ancestors were young. We know all of this, and knowing it changes everything about the experience of looking up. Let us walk through the final phase. The speculative final phase, the months and weeks before a Betelgeuse supernova. If the 4-year window is real, and if the internal clock of the star's burning sequence is running on the schedule that some researchers believe it may be running on, what would the world look like in those final months? What would we know, and what would we not know? What would the instruments be telling us, and what would we be able to do with that information? The honest answer is that we might not know anything at all until the neutrino burst arrives. This is the darkest possibility from a predictive standpoint, that Betelgeuse continues its erratic but unresolved behavior right up to the moment of core collapse, giving us no clear precursor signal, no unambiguous warning, no period of elevated certainty before the event itself. The star has been behaving unusually for half a decade, and it has not exploded. The unusual behavior might continue for another decade or another century without resolving into the terminal event. Stars do not consult our prediction intervals before they collapse. The uncertainty is genuine and irreducible with current technology. If Betelgeuse collapses tonight or tomorrow or next year, the first definitive signal will be the neutrino burst detected by underground observatories, and the gap between that signal and the visible brightening of the sky will be somewhere between 1 and 3 hours, depending on the exact stellar structure at the time of collapse. But there is another possibility. The one that would make the final phase feel more like what our intuitions demand of a countdown. Some theoretical models and some observational evidence from other massive stars suggest that a red supergiant in the very late stages of its nuclear burning sequence may exhibit elevated mass loss and increased luminosity fluctuations in the months to years before core collapse. This pre-supernova activity, if it occurs in Betelgeuse, it would be detectable against the background of the star's known erratic behavior only if it exceeds the amplitude and character of what we have already observed. A sudden dramatic increase in mass loss detectable in the infrared and radio emission from the circumstellar dust, combined with a systematic brightening or a qualitative change in the pulsation behavior, might constitute a recognizable precursor signal. It would not be a certainty. It would not allow us to say the explosion is happening in 3 weeks on a Tuesday, but it might allow us to say that the probability has shifted dramatically, that the instruments need to be repositioned, that the alert systems need to be primed, that the world needs to be told that something may be coming. Imagine that moment. Imagine the conversation that would happen between the researchers who first recognize the signal pattern as qualitatively different from everything that came before, who run the analysis, who check it against every alternative explanation and find the alternatives wanting, who call each other at unusual hours and speak in the careful, hedged language of people who understand exactly how extraordinary their claim is and exactly what the standards of evidence require. Imagine the paper that gets written, the rapid peer review process, the decision about whether to issue a public statement, the conversation between astronomers and science communicators and journalists about how to convey genuine uncertainty without causing panic or dismissing something real. Imagine the press conference, the headlines, the immediate explosion of public attention directed at a reddish star in Orion that most people walking down the street could not locate without help. And then imagine the waiting, because even in the most favorable precursor scenario, the waiting would be real. Weeks, perhaps months of knowing that something may be imminent without knowing exactly when. The star continuing to do its strange, turbulent, ambiguous thing in the shoulder of Orion while the whole world begins to pay attention in a way it never has before. Night after night of people going outside and looking up and finding the star, perhaps for the first time, and standing there in the cold or the warmth of whatever season it happens to be, looking at a point of reddish light and understanding, in whatever degree their knowledge allows, that they are looking at something that is about to end. Schools would teach it, not because they planned to, but because every child would come to school asking about it and every teacher would have to decide how to answer. Museums and planetariums would reconfigure their programming. The Orion constellation would become the most searched astronomical term in human history. Telescope sales would surge. The dark sky sites outside every major city would fill with people who had never gone to one before, who had driven an hour or two out of the light-polluted urban core to find a field or a hillside from which the sky is actually dark, and who would stand there looking at the brightest familiar stars and finding Orion and finding Betelgeuse and staying longer than they planned, because the sky, once actually seen, is harder to leave than they expected. This is one of the things a Betelgeuse supernova would do to human culture, regardless of when it happens. Even during the waiting period, even in the speculative precursor phase, even before a single photon of the actual explosion has crossed the 700 light-years between there and here. It would redirect attention upward. It would remind an enormous number of people simultaneously that the night sky exists, that it contains things with names and histories and futures, that the universe did not stop at the edge of the atmosphere. In a civilization that has largely urbanized itself into light pollution and screened itself into indoor life, the enforced awareness of a dying star would be a genuinely unusual cultural event, a collective experience of the cosmic scale that is normally reserved for the small fraction of people who actively seek it out. And then, on some specific night, in some specific second, the neutrino burst would arrive, not with a sound, not with a feeling, not with any sensation perceptible to an unassisted human nervous system. It would arrive as a flood of data pouring into the readout systems of underground observatories in Japan and Antarctica and Canada and Italy and elsewhere simultaneously. The detection algorithms trained to recognize exactly this pattern would flag the event within seconds. The automated alert systems, which have been tested and refined specifically for this scenario, would broadcast to every connected observatory and research institution within minutes, and in those minutes, before anyone without access to a neutrino detector knew anything had changed, the star that caused it would still look the same to every telescope pointed at it. The collapse would be complete. The shock wave would be travelling outward through the stellar layers. The star's surface would not yet show it. There would be a window, perhaps an hour or two, during which only the neutrino detectors knew, during which the universe had already changed, irrevocably and completely, and the light that would tell the world was still making its way to the surface of a star that no longer had a living core. Then the shock breakout, a brief, intense pulse of X-ray and ultraviolet radiation, are visible to space observatories in the right wavelength bands as the shock wave punches through the stellar surface. This pulse lasts minutes to hours. Space telescopes with automated pointing systems pre-positioned by the neutrino alert would catch it in real time. The data would show without ambiguity that the explosion has begun, and the optical brightening, the part visible to the naked eye, would begin shortly after, initially slow, then accelerating, the star's apparent magnitude climbing hour by hour through the night. If it happens during local daytime for a given hemisphere, the first people to see it with naked eyes would be those in regions where night has already fallen. Within hours, as Earth rotates, every person on the planet would have access to it. The brightening would be rapid enough in the first day or two that even casual observers checking the sky every few hours would be able to see it changing. A point of light in Orion growing visibly brighter, hour by hour. Something that does not happen with stars, something that immediately communicates wrongness and extraordinariness to anyone paying attention. By the second day, it would be bright enough to see in twilight. By the end of the first week, it would be visible in full daylight if you knew exactly where to look. By peak brightness 2 to 4 weeks after the collapse, it would need no seeking. It would be there, obvious and overwhelming, a second light in the daytime sky, casting faint shadows, blazing in the nighttime sky with a brightness that made everything familiar about the night strange. But the sounds of cities would change, not because of the supernova itself, but because of what people would do. People would go outside, in numbers that have no modern precedent for an astronomical event, not the 2017 eclipse, not the Hale-Bopp comet, nothing. People would simply go outside and look up. In the middle of the night, in neighborhoods where streetlights usually mean no one looks at the sky, people would be standing on sidewalks and rooftops, and in parks, looking at a star that had not existed in that form the week before, that was not supposed to be there. That was there anyway, blazing with the light of 100 million suns, diminished by 700 light years of travel to something still brighter than anything else in the sky. Children, born in that month, would grow up knowing that they were born under the supernova. Its adults who watched it would carry the memory for the rest of their lives in the category of moments, the category that holds the things you remember exactly where you were, and what the air smelled like, and who you were with. The oldest people alive, who had grown up looking at Orion as a fixed and permanent thing, would experience something they had never expected to experience: the actual change of the night sky within a single human lifetime. Not the theoretical change that astronomers describe when they talk about stellar evolution on million-year timescales, but the visible, undeniable, right there change of a familiar constellation rearranging itself while they watched. In the weeks following peak brightness, the light would begin to fade, slowly at first, then more rapidly, following the radioactive decay curve of nickel-56 that every supernova light curve traces with the precision of a physical law. Astronomers would be measuring the decline obsessively, comparing it to theoretical predictions, using it to constrain the mass of radioactive material ejected, building models of the explosion energy and the structure of the stellar layers. The fading would be gradual enough that for months Betelgeuse, or rather the point of light where Betelgeuse used to be, would remain the brightest star in the sky by a large margin. It would still be visible to the naked eye for many months, perhaps more than a year, before fading below the threshold of unaided vision and becoming a telescope object. During those months, a transformation would be occurring that is invisible to the eye but detectable to instruments. The expanding shell of ejected material, moving outward at tens of thousands of kilometers per second, would be pushing into the surrounding circumstellar medium that Betelgeuse shed during its centuries as a red supergiant. The collision between the fast-moving ejector and the slower, denser, circumstellar material would light up in radio waves and X-rays, creating a young supernova remnant that radio and X-ray telescopes would track with increasing resolution as it grew. In the first years, this remnant would be too small to resolve spatially. It would appear as a point source growing in flux. Within a decade, the largest radio telescopes would begin to resolve its structure. Within a century, it would be visible in broad outline to amateur telescopes. The neutron star, if one forms, and if it is observable as a pulsar, might take years to decades to become detectable as the initial chaos of the explosion settles and the compact remnant begins to emit its characteristic beams of radio emission. The 1987 supernova remnant in the Large Magellanic Cloud is still hiding its compact remnant from direct detection, though its presence is inferred from the behavior of the surrounding gas. A Betelgeuse remnant would be watched with far greater sensitivity, and any neutron star within it would be detected far more quickly. The discovery of a pulsar in the Betelgeuse remnant would be one of the great scientific moments of the post-explosion era. A direct observation of the object that the explosion left behind, a real-time confirmation of the theoretical framework that connects core collapse to neutron star formation. What happens to the sky, to Orion, in the decades after the explosion? This is the long tail of our countdown. Not the dramatic peak, not the breathless first weeks, but the slow normalization of an extraordinary event into a new ordinary. Within a year or two, the direct light of the explosion would have faded to invisibility for naked eye observers, and Orion would reassert itself as a familiar pattern with a conspicuous absence. The star that anchored the upper left of the constellation would be gone. In its place, to a telescope, would be a faint, expanding smudge of glowing gas, young, energetic, brightening in radio wavelengths even as it fades in visible light. For a generation of people who grew up after the explosion, Orion without Betelgeuse would simply be Orion. The way it looks, the way it has always looked in their experience. For the generation who watched the explosion, the absence would never be ordinary. They would always be aware of the missing star, the way you are always aware of a missing tooth with your tongue, even when you have stopped thinking about it consciously. The deeper cultural changes would unfold slowly. The event would have normalized astronomical awareness in a way that persists in the educational systems, the museum programs, the popular science culture that took root during the months of global attention. The question of what else is up there, what else is counting down, what other star might be the next Betelgeuse? That question would not fade with the fading of the supernova's light. It would remain embedded in a generation that watched a star die in real time and understood for the first time, viscerally and personally, that the night sky is not a fixed backdrop, but a dynamic, evolving, event-filled universe in which things happen on timescales that intersect with human lifetimes. That understanding is one of the things this countdown is really about, not just the physics of Betelgeuse, though the physics is extraordinary, not just the timeline of its death, though the timeline is what gives the story its structure and its urgency, but the shift in perspective that comes from genuinely reckoning with the idea that the universe is doing things right now. Things with measurable schedules and predictable phases and observable consequences. Things that have been running since before we existed and that will continue long after we are gone. Things that we can understand and measure and predict with the tools that science has built over the last few centuries. That shift in perspective, from the sky as a painting, a fixed and permanent backdrop for human activity, to the sky as a process, a living, evolving system of countdowns and events and phases, is perhaps the most important thing that modern astronomy offers to anyone willing to really absorb it. You are living through one of those countdowns right now. Not just the Betelgeuse countdown, though that one is the most immediate and the most spectacular. You are living through the sun's long countdown to its eventual death, a countdown measured in billions of years, but running nonetheless. Is ticking off each second of fusion with the same inexorability as Betelgeuse's shorter clock. You are living through Earth's countdown to the point where the increasing solar luminosity makes the surface uninhabitable. 1 billion years from now, roughly, by current estimates. You are living through the countdown to the Andromeda merger, 4.5 billion years away. You are living through the countdown to the end of the Stelliferous era, 100 trillion years away. You are living through the countdown to the heat death of the universe, 10 to the power of 100 years away. Every one of these clocks is running. Every one of these events is coming, and you are here. Right now, in the window between the beginning and all of those endings, in the brief, extraordinary, cosmically improbable moment when the universe has organized itself into something capable of knowing that all of this is happening. That is the thing that sits at the heart of every video this channel makes, and it sits at the heart of this one too. The countdown to Betelgeuse is not really about Betelgeuse. It is about time, about what it means to exist inside time, to be subject to its passage, to watch things begin and begin again in forms we might not recognize. We are creatures of a particular time scale. We live in decades, we remember centuries, we can barely imagine millennia. The timescales of stellar evolution, of galactic dynamics, of cosmic thermodynamics, these are not timescales we can feel. We can only think our way into them using the tools of mathematics and physics and the strange, persistent human capacity for abstract contemplation of things larger than our experience. And when Betelgeuse explodes, whenever it explodes, whether in 4 years or 40,000, it will be the universe's reminder that those abstract contemplations are connected to something real, that the numbers are not just numbers, that the countdown is not a metaphor, that something is actually coming, and when it arrives, it will be visible from your backyard and You will not need a textbook or a telescope or a degree in astrophysics to know that you are looking at something that matters. You will need only to go outside and look up, which is something human beings have been doing for as long as they have been human, in every culture, on every continent, under every sky. With every variety of understanding and ignorance and wonder and fear and curiosity that the human animal is capable of bringing to the act of raising its eyes toward the dark. The star is there tonight. It has been there every clear winter night for as long as anyone alive can remember. It was there for your parents and their parents and every generation stretching back through the full recorded history of human civilization and beyond, into the deep time before writing, before cities, before agriculture, when the people who looked at it did not know its name or its nature, but recognized its redness and its position and built it into their stories the way all people build the enduring things around them into their stories. It has been burning for 10 million years. It has been dying for a long time. And it may have only a short time left, or a long time, or anything in between. We do not know. That is the truth at the center of this countdown, and it is a truth worth sitting with rather than rushing past. Go outside tonight, if the sky is clear, where you are. Find Orion. The belt of 3 stars is the easiest guide, rising in the east in winter months, climbing to its highest point in the south at midnight, setting in the west before dawn. Look to the upper left of the belt. Find the reddish star, not brilliant white like Rigel at the lower right, but warm orange-red, the color of an ember. That is Betelgeuse. The light you are seeing left that star somewhere around the year 1325. The King of France was Louis X. The Holy Roman Emperor was Louis IV. The Aztec city of Tenochtitlan had not yet been founded. The Black Death had not yet swept Europe. The light leaving that star tonight will not arrive at Earth until somewhere around the year 2725. Whatever is happening at Betelgeuse right now, whatever stage the core has reached, whatever balance is being maintained or has already broken, we will not know for 700 years. But what left that star 700 years ago is here now, reaching your eye, crossing 700 light years of space to fall on the retina of a creature that evolved on a small rocky planet orbiting a modest yellow star in the outer arm of a spiral galaxy. A creature that looked up, recognized the light for what it was, learned the name of the star it came from, calculated the star's distance and mass and internal temperature and remaining lifespan, built instruments to measure its neutrinos and image its surface and track its pulsations, and sat down one night to explain all of this to other members of its species in the hope that the explanation would mean something to them, would give them something to carry into their day or their night or their sleep, some expanded sense of what they are part of, some feeling for the scale of things, some awareness that the ordinary sky is not ordinary at all, that it is full of history and physics and time and events on every scale from the human to the cosmic, and that one of those events, one of the most spectacular ones our species may ever witness, may be coming soon. The countdown is real. The physics is real. The star is real. And you, looking up at it from wherever you are. On whatever night you find your way outside and find Orion and find that reddish point of light, you are real too. Conscious matter, looking at dying matter across 700 years of traveling light. Understanding something about what it is seeing, that is the most extraordinary thing in this entire story. Not the supernova, not the shock wave or the neutrino burst or the centuries-long nebula or the neutron star cooling in the dark. The most extraordinary thing is that we know, that we figured it out, that we built the tools and the mathematics and the patience to look at a point of light and know what it is, what it contains, what it is doing, what it will do, and what it will leave behind. Betelgeuse is counting down, and we are here, counting with it.